Hello, my dear students. Welcome to the second lecture of electrostatic potential and capacitance. Today, we'll discuss the MCQ questions of equipotential surface. The first question from the MTG fingertips book. Consider a uniform electric field in the z direction. The potential is a constant. So, let's draw the coordinate system first. Here in this particular case, okay, here assume that this is z, this is x, and this is y. So x, y, z here we have taken, and assume that electric field lines are along the z direction, as it is given the question. Electric field lines are along z direction, and assume them to be constant over here. So that means it is uniform electric field along z direction. Clear? So in that particular case, what it is saying, which of the following is true? So here in this particular case, we know that if field lines are along z direction, or if field lines are uniform or they are parallel to each other, then in that particular case the equipotential surfaces will be the plane surface. Clear? So if we draw the equipotential surface for this particular one, so this will be plane surfaces, and these plane surfaces will lie in the xy plane. Here these plane surfaces will lie in the xy plane. For example, suppose I'll be copying that one. So this will be the plane surfaces. Okay, so here in this particular case, that means these are the plane surfaces. These are the plane surfaces in xy plane. Clear? So these are equipotential surface. So here in this particular case, what the first option is saying is that for any x for a given z, that means potential is constant for any x. Potential is constant at any x for a given value of z. So suppose if we will take this second surface. So at this particular value of z, what will be the value of potential at any values of x? It means for any value. That means at this particular z, if we move along x direction, that means along x means if we move upward at this point, or over here, or over here, as all these points are present on this equipotential surface. Clear? So that means here in this particular case the potential will remain constant. That means here this particular option is true. Clear? तो यहाँ पे एक z का एक पर्टिकुलर वैल्यू पे अगर हम x डायरेक्शन में मूव करेंगे, क्लियर, फॉर ए पर्टिकुलर वैल्यू ऑफ z अगर हम x डायरेक्शन में मूव करेंगे, मतलब कि हम ऊपर की तरफ मूव कर सकते हैं. क्लियर? सो एट दैट मीन्स ऑल दिस पॉइंट्स विल लाई ऑन ए पर्टिकुलर इक्विपोटेंशियल सरफेस. दैट मीन्स तो ये सब केसेस में ये सब पॉइंट पे हमारा पोटेंशियल क्या होगा, सेम रहेगा. क्लियर? एंड नेक्स्ट, मूविंग टू द नेक्स्ट, फॉर एनी y for a given z, that means potential is constant for any y. Suppose if I'll consider this particular value of z over this value of z. Clear? So that means at this particular value of z, if I move along y-axis, clear, if I'm moving along y-axis, that means where how can I move along y-axis? That means I can move like this, or I can move like this. Clear? So here in this particular case, what it is saying is that whether potential will remain constant for any value of y or not, for a given particular value of z. तो यहाँ पे एक पर्टिकुलर वैल्यू ऑफ जेड में ले रहा हूँ, और उसके साथ में क्या कर रहा हूँ, मैं वाई के अलॉन्ग मूव कर रहा हूँ. क्लियर? आइदर पॉजिटिव वाई और नेगेटिव वाई. क्लियर? So that means here you can see that all these points will lie on this particular surface, which is an equipotential surface. That means here in this particular case this is also true. Clear? ये भी यहाँ पे true होगा. And next option C, on the xy plane for a given z. That means on the xy plane, suppose if I'll take any particular value of z, over here, for example, suppose if I'll be taking at this particular value of z, clear? If I, that means uh, at this particular value of z, this is a particular equipotential surface, for example, or else you can say what is the location of this equipotential surface. This equipotential surface might be located somewhere else over here at this particular value of z. और ये जो सेकंड इक्विपोटेंशियल सरफेस है, ये इसका जो ये कहाँ पे लोकेटेड है, दिस विल बी लोकेटेड समवेयर एल्स ओवर हियर, यहाँ पे कहीं पे. और ये जो इक्विपोटेंशियल सरफेस है, ये नेगेटिव जेड में यहाँ पे कहीं पे हमें मिलेगा इसका लोकेशन, ये जगह पर. क्लियर? सो इसमें ये बोला है कि एक पर्टिकुलर वैल्यू एट एनी पर्टिकुलर वैल्यू ऑफ जेड इन द एक्स वाई प्लेन. तो ये जेड पर ये एक्स वाई प्लेन जो हमें मिला ये वाला, तो इसमें हमारा पोटेंशियल कांस्टेंट रहेगा. आप कोई भी लोकेशन इधर उधर कहीं भी आप जा सकते हो, इस लोकेशन पर आपको पोटेंशियल सेम मिलेगा. दैट इज ऑल्सो ट्रू. क्लियर? So here that means all the options A, B, C are true. That means option D, it is saying all of this. That means option D will be the correct option for this one. Moving to the second question. Equipotential surfaces. Okay, so tell us about from these options which one will be correct. So which one is correct about the equipotential surface? Equipotential surfaces are closer in regions of large electric fields compared to regions of lower electric fields. Clear? So that is true. Why? Because it is a property of equipotential surface. We know that suppose if I'll be taking one positive charge. Clear? So if I'll be drawing the equipotential surface due to this positive charge, then this will look like this. So equipotential surface due to positive charge. Gradually the spacing between the equipotential surfaces will increase. Gradually what will happen? The spacing between the equipotential surfaces will increase. That means here we know that we know that near the given charge, clear, or you can say at very close to the charge, clear, at a point which is very close to the charge, electric field strength is more. Clear? Electric field strength is more. If electric field strength is more, then in that particular case that means here how can you say that electric field strength is more? Because the density of field lines will be more. Clear? Similarly here in this particular case, the equipotential surfaces, suppose this if you see the first three equipotential space, this 1, 2 and 3, then spacing between them is gradually increasing. Here spacing between the first two, if it is D, then next two will be D prime, and next two it will be D double prime, and next two it will be D triple prime. That means here D triple prime will be greater than D double prime, greater than D prime, greater than D. That means spacing will gradually increase. So here in this particular case, near the charge field strength is more, near the charge equipotential surfaces will be closer together. Clear? So that means option A is the correct one. Will be equipotential surfaces will be more crowded near sharp edges of a conductor. Okay, so here in this particular case, this is a very important concept. Suppose if I be taking one conductor like this. Clear? Here in this particular case, I'll be taking one conductor to be like this, and if I'll be if I'll be giving some charge to it, the amount of positive charge, then what will be the distribution of the charges? So when you give some q amount of charge, the distribution of charges will be like this. You can see over here at the sharp edges, the charges, more number of charges are gathered over there. Here where there is sharp edges, you can see maximum number of charges will gather over there, but where there is flat surfaces, the spacing between the charges generally increases. Why that is the case, and how can you say that that spacing will increase in some location and spacing will decrease in some location? That you can say from the surface charge density. We know that surface charge density is nothing but charge divided by area. Clear? So charge, if it is, if we'll assume, if we assume, if we take a particular curve here over here, if we take a particular curvature over here, then we can find out the radius of curvature. Clear? So here in this particular case, that means the surface charge density can be written as q upon 4 pi r square. Clear? So this flat surface over here, suppose, so if I'll be drawing one imaginary kind of sphere, clear, imaginary kind of sphere, then it will be like this. Clear? So that means that curvature part will be having one radius, that let it be r. Clear? So that is the radius of curvature of this curve. Similarly, if I'll be taking this particular curve over here, this particular curve if I'll be taking, then the imaginary kind of sphere will be very small. Clear? That imaginary kind of sphere will be very small. That means its radius will be small. That means if radius decreases, surface charge density will increase. Clear? If radius increases, surface charge density, if radius increases, then surface charge density will decrease. If radius increases, then this surface charge density will decrease. Clear? So here in this particular case, remember that if you are looking at this small curve part where there will be sharp edges जहाँ पे रहेगा वहाँ पे कर्वेचर, रेडियस ऑफ कर्वेचर कम रहेगा. रेडियस ऑफ कर्वेचर कम रह रहा है, उसका मतलब है सरफेस चार्ज डेंसिटी वहाँ पे क्या होगा, ज़्यादा होगा. मतलब वहाँ पे मोर नंबर ऑफ चार्जेस विल गैदर ओवर देयर. ओके, सो व्हाट इज सेइंग, equipotential surfaces will be more crowded नियर शार्प एजेस ऑफ ए कंडक्टर. तो शार्प एजेस में क्या होता है, शार्प एजेस में मैक्सिमम नंबर ऑफ चार्जेस वहाँ पे गैदर होते हैं. तो अगर मैक्सिमम चार्जेस वहाँ पे गैदर होते हैं तो उस रीजन में हमारा जो चार्ज का जो मैग्नीट्यूड है वो इंक्रीज कर, मैग्नीट्यूड ऑफ चार्ज इंक्रीजेस. क्लियर? और उसके साथ साथ क्या होता है कि रेडियस ऑफ कर्वेचर ऑफ द गिवन जो शार्प एजेस है उसका जो रेडियस ऑफ कर्वेचर वहाँ पे क्या होता है, दैट ऑल्सो डिक्रीजेस. क्लियर? तो फाइनली क्या होगा, सरफेस चार्ज डेंसिटी वहाँ पे ज़्यादा होगा. क्लियर? और यू कैन से फ्रॉम देयर कि चार्ज ज़्यादा है, चार्ज का मैग्नीट्यूड अगर ज़्यादा है तो उसके जो नियर वाला रीजन है उसमें इक्विपोटेंशियल सरफेस के बीच में स्पेसिंग वहाँ पे कम होगा. क्लियर? सो दैट्स वाई इक्विपोटेंशियल सरफेसेस विल बी मोर क्राउडेड नियर द शार्प एजेस ऑफ ए कंडक्टर. तो यहाँ पे जो इक्विपोटेंशियल सरफेस फॉर्मेशन होगा वहाँ पे क्राउडिंग थोड़ा ज़्यादा होगा, और ये वाला जो फ्लैट सरफेस है इसके वजह से जो इक्विपोटेंशियल सरफेसेस फॉर्मेशन होगा वहाँ पे क्राउडिंग आपको कम मिलेगा. क्लियर? तो इसका ये वाला ऑप्शन हमारा क्या है, यहाँ पे सही होगा. नेक्स्ट ऑप्शन सी, विल इक्विपोटेंशियल सरफेसेस विल ऑलवेज बी इक्वली स्पेस्ड. यहाँ पे ये बोला जा रहा है कि जो इक्विपोटेंशियल सरफेस होगा वो हमेशा इक्वली स्पेस्ड होगा. इक्वली स्पेस्ड मतलब हर एक इक्विपोटेंशियल सरफेस के बीच में जो डिस्टेंस है दैट विल रिमेन कांस्टेंट. दैट डिस्टेंस विल ऑलवेज रिमेन कांस्टेंट. क्लियर? यहाँ पे बोला जा रहा है कि ये डी होगा तो ये डी होगा, और ये कब वैलिड हो सकता है, जब आपका फील्ड वहाँ पे यूनिफॉर्म हो. क्लियर? But if you just look at the field, the equipotential surfaces figure, due to a positive charge here, spacing is not same. Why spacing is not same? Because here electric field is not uniform. Gradually, as you move away from the charge, field strength decreases. So due to that one, what happens? The spacing between the equipotential surfaces gradually increases. Clear? So यहाँ पे ये वाला जो option है, option C will be the wrong one. So both A and B are correct. So here what option D is saying, both A and B are correct, so we will choose option number D over here. Next, moving to question number 25. In a region of constant potential, जहाँ पे हमारा पोटेंशियल कांस्टेंट होगा, तो उसको कौन सा यहाँ पे ऑप्शन यहाँ पे सही तरीके से डिस्क्राइब कर रहा है. क्लियर? So option A, what is saying, the electric field is uniform in a region of constant potential. Okay, fine. So where will you get a constant potential? Okay, so first of all, let us take a spherical conductor. Clear? This is what, this is a spherical conducting cell, or conducting spherical cell, you can say. Clear? And it will be having some radius, let it be r. Suppose if I'll be giving some charge to it from outside, then these charges will distribute automatically. These charges will distribute automatically on the surface of the given conducting body. Clear? Then in that particular case, what actually happens is that as no charges reside inside the given conductor, then inside the conductor electric field is zero. Clear? And if electric field is zero, then in that particular case we can say that no charge is inside the conductor. That means electric field inside, charge inside, that remains zero. Clear? So here if electric field inside is zero, then what we can say, we know the relationship between E and V as E equal to minus dV by dr. So magnitude of E will be nothing but dV by dr. Clear? But E inside if it is zero, E inside if it is zero, that means dV by dr equal to zero. That means rate of change of which type of quantity will be zero. So rate of change of a constant quantity will be zero. That means potential must be constant over there. That means in that region V must be constant. ये आपको याद रखना है, ये तीनों terms. Clear? So a conducting cell, if you are taking a conducting cell or solid conducting sphere, clear, that is valid for both, or solid conducting sphere, ये दोनों केस में. क्लियर? तो इसमें हमें ये याद रखना है, ये तीनों चीज़ हमें ध्यान में रखना है कि कोई भी चार्ज अगर हम देते हैं तो नो चार्जेस विल रिसाइड इनसाइड द कंडक्टर. इनसाइड द कंडक्टर इलेक्ट्रिक फील्ड विल बी जीरो, देन पोटेंशियल विल बी कांस्टेंट. दैट मीन्स this conducting sphere will behave as a equipotential surface. दिस विल बिहेव एज इक्विपोटेंशियल सरफेस. मतलब सेंटर पर पोटेंशियल जितना होगा, इस लोकेशन पे पोटेंशियल उतना होगा, यहाँ पे भी पोटेंशियल उतना होगा, हर जगह आपको पोटेंशियल यहाँ पे सेम मिलेगा. सो व्हाट इज सेइंग, इन ए रीजन ऑफ कांस्टेंट पोटेंशियल, तो दिस फॉर्म से रीजन ऑफ कांस्टेंट पोटेंशियल इलेक्ट्रिक फील्ड इज यूनिफॉर्म. तो इलेक्ट्रिक फील्ड यूनिफॉर्म कैसे होगा? यहाँ पे तो इलेक्ट्रिक फील्ड हमारा जीरो है. क्लियर? इलेक्ट्रिक फील्ड जीरो आप कैसे प्रूव करोगे? बाय टेकिंग द गॉस लॉ लेके भी आप उसको प्रूव कर सकते हो. क्लियर? तो गॉस लॉ लेके आप कैसे उसको प्रूव करोगे? यहाँ पे इस वाले केस में थोड़ा बहुत ध्यान में रखो. सपोज हम इस जगह पर इलेक्ट्रिक फील्ड निकालना चाहते हैं, तो उसके लिए हमें क्या करना पड़ेगा? वी हैव टू कंस्ट्रक्ट व्हाट वी हैव टू डू, वी हैव टू कंस्ट्रक्ट ए गॉसियन सरफेस. एक गॉसियन सरफेस जो कि यहाँ पे स्फीयर होगा. क्लियर? और वो भी आर रेडियस का गॉसियन सरफेस आपको यहाँ पे कंसिडर करना पड़ेगा. क्लियर? तो अगर आप यहाँ पे गॉस लॉ अप्लाई करोगे तो गॉस लॉ क्या होगा? क्लोज सरफेस इंटीग्रल ई डॉट ds इक्वल टू चार्ज एनक्लोज डिवाइडेड बाई एप्सिलॉन नॉट. तो इस जगह पे ध्यान में रखो कि ये जो गॉसियन सरफेस है ये कितना चार्ज अभी एनक्लोज कर रहा है? नो चार्ज. यहाँ पे कुछ भी चार्ज नहीं है तो जीरो चार्ज. तो फाइनली इलेक्ट्रिक फील्ड हमें कितना मिलेगा? जीरो मिलेगा. क्लियर? नो नीड टू डू एनी कैलकुलेशन. सो रिमेंबर दैट वन. सो इलेक्ट्रिक फील्ड इज यूनिफॉर्म, दैट इज रॉन्ग. इलेक्ट्रिक फील्ड इज जीरो, that is correct. There can be no charge inside the region, that is also correct, because we have just already said that no charges, surface के अंदर में कोई भी चार्ज नहीं रहेगा, so that will be also be correct. So option D, what is saying, both B and C are correct, so here we will choose option number D, which will be the correct one. Next question number 26, which of the following statement is true about the relation between electric field and potential? So generally we know that there is a standard relationship between electric field and potential, and that relationship is equal to minus dV by dr. Generally this electric field is a vector quantity and this whole term is a vector quantity. Here this is called, and we also can write this electric field in higher standard mathematics, in higher classes mathematics, by taking the help of that one. We can write that one is equal to LV. Clear? This is called gradient operator. This is called gradient operator. Clear? As it is not there in for the students of 12th standard or 11th standard. so we will not go through that one. So but just remember that this is a operator which is when it will operate upon any scalar quantity, here's potential is a scalar quantity, then it will give you a vector quantity. Clear? So this is called gradient operator. That's why how will you read this particular relation? So here it is said that electric field is the negative as negative sign is there, negative gradient is the negative gradient of potential, is the negative gradient of potential, or you can say potential difference is the negative gradient of potential or potential difference. So here based upon that one we'll choose check the options. Option A, electric field is in the direction in which potential decreases the steepest. Clear? So this particular term what it's saying is that, so here how can we prove that this electric field due to the positive charge, suppose this is the positive charge and the field is away from the charge, so how can we say that this electric field is along the direction of decreasing potential? Clear? That means here if potential, let the potential over here be v1 and potential of the surface let it be v2, this is the 2D view, and potential over here let it be v3, that means v1 will be greater than v2 greater than v3. So that means electric field is along the direction of decreasing potential. So how will you prove that one? So assume that this is some electric field that means electric field lines are parallel to each other. So that means what it will say, it will say that the equipotential surface with the plane surface. So this is the 2D view. In 2D view, suppose this is a region A, this is region A, and let it be region B. Suppose that means as these field lines are moving from left to right, that means there must be a positive charge somewhere else at infinite. Clear? So if it is the case, then what is the potential difference between A and B? Clear? Suppose here we want to find out the potential difference between A and B. So let potential at A, at this particular location, potential at A be VA and potential at B be VB. Suppose if I want to find out the potential difference over here, VA minus VB, suppose, then what do I have to write? I have to write down simply E dot dr, or else you can use the general formula which suppose if I'll be writing over here potential difference, I'll be taking means, suppose if I'll be considering the motion from A to B, suppose if I'll be considering the motion of any particular test charge, suppose if I'll be taking a test charge q naught and its motion from A to B, that means here in that particular case that potential difference will be VB minus VA. Clear? So if it is VB minus VA, then in that particular case what will be writing? Negative of line integral of E dot dr. Clear? So here in this particular case electric field is towards right, and displacement, let the displacement from A to B, that displacement is D over here. Clear? So that means here in this particular case negative of E dot dr, that means electric field is towards right and displacement is also towards right, that means it will be simply negative of E dr, and assuming for a small displacement this electric field to be constant, that means we can take E outside, that means negative of E integral dr. So that means it will be minus E into D, that means the displacement will be simply considered as D. So that means here in this particular case what we are getting, VB minus VA is negative. If VB minus VA is negative, that means here in this particular case what you can say, VA minus VB will be positive. So that means potential at A will be greater than potential at B. So that means this electric field is along the direction of decreasing potential. But according to the first property, where, or you can say one property that is there in case of equipotential surface, what is that property? वो property क्या बोलता है? उसमें ये बोला जाता है कि electric field is always perpendicular to the equipotential surface. Electric field lines are always perpendicular to the equipotential surface. That means here we can say that the means electric field lines are along the direction of decreasing potential, but that field lines will be perpendicular to the equipotential surface. That means what you can say, alternate definition wise, alternately what you can say, that potential equipotential surfaces, or you can say electric field lines are along the direction of decreasing potential, or here this particular statement what it's saying, electric field is in the direction in which potential decreases the steepest. Potential decreases the steepest, उसका मतलब ये है कि जहाँ पे पोटेंशियल आपका जल्दी स्टीपली मतलब एब्रुप्टली सडनली डिक्रीज हो रहा होगा, उसी डायरेक्शन में हमारा फील्ड रहेगा. जहाँ पे पोटेंशियल हमारा एब्रुप्टली ग्रेजुअली मतलब स्लोली नहीं चेंज हो रहा होगा, मतलब एब्रुप्टली जहाँ पे चेंज हो रहा होगा, सडनली जहाँ पे चेंज हो रहा होगा, जिस डायरेक्शन पे चेंज हो रहा होगा उसी डायरेक्शन में हमारा इलेक्ट्रिक फील्ड रहेगा. तो ये वाला जो स्टेटमेंट है यहाँ पे, this statement is correct. Second is, magnitude of electric field is given by change in magnitude of potential difference per unit displacement normal to the equipotential surface at that point. That means this particular statement is telling about this relation electric field, magnitude of electric field. So if I will write down the magnitude of electric field, it will be simply dV by dr, or you can write it as delta V by delta R. Magnitude of electric field will be nothing but this one. So here in this particular case, magnitude of electric field is given by change in magnitude of potential, change in magnitude of potential per unit displacement. Per unit displacement, that means this is the displacement, and that displacement should be normal to the equipotential surface at that point. So here in this particular case, you can see the direction of electric field is normal to the equipotential surface, or you can say here in this particular case, the direction of motion of the charge particle, or you can say the displacement of the charge particle. Displacement of the charge particle is along the direction of field, and that field is perpendicular to the equipotential surface. That means the displacement of those charge particles will be perpendicular to the direction, or perpendicular to the equipotential surface. So here this particular statement, it is also true. Next, in option C, in the region of strong electric field, equipotential surfaces are far apart. So already we have discussed. That means where the field is strong, there equipotential surfaces spacing between the equipotential surface is less. Where field is weak, spacing between the equipotential surfaces will be more. So that means option C will be the wrong one. And option D, both the statement A and B are correct. That means A and B are true. So here in this particular case, we will choose option number D. Next, in question number 27, what is the angle between electric field and equipotential surface? Clear? So as we know that there is a property about this particular concept for equipotential surface, electric field lines are always perpendicular. Electric field lines are always perpendicular to the equipotential surface. Electric field lines are always perpendicular to the equipotential surface. That means they make 90-degree angle. That means option A will be the correct one. Okay, here in question number 28, the work done to move a unit charge along an equipotential surface from P to Q. First option must be defined as this one, line integral from P to Q E dot dl, and that work done is 0, can have a non-zero value. Both A and B are correct. So here, generally in normal cases, how will we define the work done? Here, work done. So we know that potential difference, or generally potential. How do we define the potential? Potential is defined as negative of line integral of electric field E dot dl. Clear? So here in this particular case, what will be the potential difference between the two given locations? Suppose there are two. Suppose there is a positive charge over here, and due to that one, we are taking two locations as this one. So here will be P, and this will. So here in this particular case, what will be the work done to move the charge from P to Q over a displacement of dl? let the displacement over here is dl from P to Q is d. So here in this particular case, this is the potential difference. This is how we define the potential. Then work done will be equal to Q into V. So it will be Q into V is negative of line integral of E dot dl. But the magnitude of charge, what they are saying is that unit charge, unit positive charge. That means that charge will be, magnitude of that charge will be taken as 1 unit. Clear? So if it is that the case, then W will be equal to line integral of E dot dl with negative sign over there. So finally, so from whatever the limits over here, we are taking the charge from P to Q. That means the limits will be from P to Q. So this is how we can define the work done in moving a unit charge. Clear? So work done in moving a unit charge. But here what it is saying is that it is an equipotential surface. Here what it is saying, it is an equipotential surface. But we know that for an equipotential surface, work done in moving a charge over an equipotential surface is 0. So here these two options will be correct. So this is how we define the work done in moving a charge, and this is the result of that particular case. Clear? This is the result of that particular case. Why? Because work done in moving a charge over an equipotential surface, that means potential difference at over an equipotential surface will be 0. That means this term will become 0. So no need to do all these things. Clear? Potential difference directly, that will be 0. So finally work done will be 0 over there. So option A and B are correct. Option C can have a non-zero value. That means work done will be either positive and negative. It can have any non-zero value. That is wrong. Why it is wrong? Because equipotential surface is a surface where potential remains constant. So over an equipotential surface, if we take two different locations, then also that locations will be having same potential. So potential difference will be 0. If potential difference is 0, then work done will be 0. So that means here we'll choose option D, because both A and B are correct, it is saying. In question number 29, the top of atmosphere is about 400 kilovolt with respect to the surface of Earth. Okay. Corresponding to the electric field that decreases with altitude, near the surface of Earth, the field is about 100 volt per meter, and it is the potential at the top of the atmosphere. But still don't get an electric shock as we set out of our houses. जैसे ही हम घर से बाहर निकलते हैं, बट हमें बाहर निकलने से क्या होगा, हमें शॉक नहीं लगता है. Why? Clear? And what they have told is that assume the house to be free from electric field. So here in this particular case, if we consider the Earth, this is our Earth. Clear? And assume the center to be present over here somewhere else. It is Earth. Then where is our location? We are present on the surface of Earth. So we are generally, suppose if I'll be considering this is a person, suppose Ram is staying in this particular house. Clear? So this is the house of Ram. So inside it, he is there in a field free region. Why field free region? Generally इट इज़ जनरली, अगर हम यहाँ पे देखेंगे तो जो छत है, जो घर का जो छत होता है वो कंक्रीट से बना रहता है, कंक्रीट सीमेंट एज वेल एज रोड भी वहाँ पे रहता है. सो जो रोड रहता है वहाँ पे वो क्या है, कंडक्टर है, तो लोहे से बना हुआ रहता है, तो वो एक इक्विपमेंट, दैट मीन्स दैट फॉर्म्स एन इलेक्ट्रोस्टैटिक शील्डिंग. क्लियर? तो इसलिए इलेक्ट्रिक फील्ड जो है इनसाइड द होम, दैट जनरली इट इज़ एज्यूम टू बी 0. तो यहाँ पे एज्यूम किया गया है कि इलेक्ट्रिक फील्ड इनसाइड द होम इज़ 0. But as soon as he comes out, Ram comes out from the home, as soon as Ram comes out from the home, then what actually happens? Okay, इसमें और क्या information हमें दिया गया है? So what they are saying is that there is atmosphere about that means top of the atmosphere is about having 400 kilovolt atmosphere. So if we see as we move up, that means as we move away from the surface of earth, we'll get different layers of atmosphere. Different layers means you will get troposphere, stratosphere, mesosphere, ionosphere. So the top of the layer, which is nothing but which is generally known as ionosphere. Here this is, let us assume this is the top of the atmosphere. Clear? This is the top of the atmosphere, which is nothing but ionosphere. And this ionosphere generally contains the charged atoms or molecules. ये generally क्या contain करता है? This contains generally charged atoms or molecules, and the top of the atmosphere is about 400 kilovolt with respect to the surface of Earth. That means this forms an assume that this forms an equipotential surface. This is an equipotential surface having a potential of 400 kilovolt. Clear? Okay. Corresponding to that case, electric field decreases with altitude. Near the surface of Earth, the field is about 100 volt per meter. Near the surface of Earth, that means not on the surface of Earth, near the surface of Earth, here at this particular point, assume the electric field is what they are saying 100 volt per meter. Okay. So what they are saying is that when Ram comes out from his home, or when a person comes out from his home, then why don't he get any electric shock? Clear? So in this particular case, just remember that is we generally consider the potential of Earth. Potential generally it is uh, generally it is considered to be 0 volt. Here potential of Earth it is generally considered to be 0 volt. So here if potential of Earth is 0 and potential at the top of the layer of that means atmosphere is 400 kilovolt, that means there is a gradual change in the potential. Clear? As we move from the top of the atmosphere towards the surface of Earth, then this potential gradually decreases. Clear? That means there is a potential difference created between these two. Clear? So then when this person comes out from the home, then why don't he get any electric shock? So if we check the options, what the option is saying is that our body is a perfect insulator. Our body, what it is saying, it is a perfect insulator. So I think it is wrong. Why? Because generally we consider our body to be a conductor. It may not be a perfect conductor, but it is generally behaves, it sometimes behaves as a conductor, or it is a conducting body. Why? Because when you just touch any any surface or any charged body, then that charges will, then that means current will pass through the body. Clear? And it will pass through the body to the ground. Clear? So generally the body or human body is considered to be generally considered as a conductor. So option A will be wrong. Our body and ground forms an equipotential. So here when the person comes out from the home, what actually happens is that as Earth is considered to be a huge conductor, Earth is considered to be a huge conductor, and along with that a human body is also behaves as a conductor. That means the potential as the potential of the surface of Earth is considered to be 0. This is the ideal case. Generally it we conventional it is considered to be 0. That means as we are also present on an equipotential surface, that means the surface of Earth, that means our potential should clear. So that means we, that means human beings as well as the surface of Earth possess same potential. Clear? Okay. Another thing is, if we'll consider same potential means what? Over the surface of Earth at any location, over the surface of Earth at any location, potential will be 0. Over the surface at any location, potential will be 0. If potential is 0 at any location over the surface, that means when we move through along the surface, we move along the surface means we'll move like this. We will move like this. Clear? So after some time we might be over here. So here in this particular case, that means what will be the work done to move from one location to another location according to the concept of electrostatics? That work done will be 0 over here. Clear? So that one will be 0 over here because potential difference over here is 0, no potential difference. So if that, and another thing is that here, as we are considering the upper layer of atmosphere to be having 400 kilovolt, that means it is simply considered to be an equipotential region. Similarly, the surface of earth is also form an equipotential region. Then the direction of electric field, what how it will be over here. So the direction of electric field will be perpendicular to the equipotential surface. Direction of electric field will be perpendicular to the equipotential surface. So perpendicular to the equipotential surface. That means at this particular point here on the surface, this electric field, as it is perpendicular to the equipotential surface, that means there will not be any component of electric field along the surface, that means along the surface of earth. Clear? So if there is no component of electric field, then no force on the human body. Clear? If no force on the human body, then also no work will be done. Clear? So here in this particular case, we can say that our body and ground forms an equipotential surface. That's why this is the reason why we do not get any electric shock. Clear? Okay, so option B will be the correct one. Next, the original equipotential surfaces of open air remain same. Original equipotential surface of open air. For example, suppose if this is ionosphere having some potential, then gradually as we move towards the surface of earth, so we'll get some other layers of atmosphere. So their potential will gradually decrease. So different layers of other atmosphere will will be having some other potential, and that potential will be definitely less than this 400 kilovolt. Clear? So layer wise potential might remain same, but different layers will be having different potential. A single layer will be having same potential, that means at any location on the single layer might be having the same potential, but as we move from one layer to another layer, from one layer to another layer, or from one layer to another layer, then potential will definitely change. Clear? So here what is saying, the original equipotential surfaces of open air remain same. Equipotential surfaces of open air जो यहाँ पे एटमॉस्फेयर है, हर एक का यहाँ पे पोटेंशियल सेम रहेगा. So that will be the wrong. And option D, what is saying, it is saying that none of the above three are correct. So this is also wrong. So option B will be the correct. Okay, here in question number 30, what it is saying, a hollow conducting sphere is placed in an electric field. Hollow conducting sphere, this one is a hollow conducting sphere. Here, electric field produced by a point charge placed at a point. So assume that there is a point charge present over here. Clear? And this point charge will be producing some electric field. How that field will look like, these are the fields. So these are the fields. If we draw the field lines, these will be the field lines. Okay, so here in this particular case, these field lines are away from it, and within these field lines we are placing one hollow conducting sphere. Let VA, VB, VC with the potential at ABC respectively. Then what is the relationship between these two? Clear? So here in this particular case, if we just look at the figure closely, then this figure over here is wrong. Why it is wrong? Because if we just see the properties of a conductor, when you place a conductor in an electric field, in an external electric field, then what actually happens is that suppose if we take any external electric field like this, and if we place any conductor inside it, that means this will be positively charged plate and this will be the negatively charged plate. And when we place a conductor inside it, then field lines will vanish inside the conductor. There will not be any field lines. There will not be any field lines inside the conductor. No field lines. Here these field lines will vanish. Field lines will be parallel to the surface of conductor, but no field lines will be there inside the conductor. That means over here inside the conductor electric field will be 0. Clear? And inside the conductor charge will also be 0. Clear? So then what actually happens is that potential on the surface of conductor is constant. Clear? So V remains constant. That means this surface, this conductor behaves as an equipotential surface. Conductor behaves as an equipotential surface. So similarly here in this particular case also, these field lines will not be there inside the given conductor. Clear? These field lines will not exist. These field lines will not exist inside the conductor. Here also these field lines will not exist inside the conductor. Clear? So if it is does not exist inside the conductor, so in that particular case, another thing we must remember that these field lines must be perpendicular to the surface of conductor. यहाँ पे perpendicular यहाँ पर होना चाहिए. Clear? यहाँ पे ये perpendicular यहाँ से बाहर निकल के जाना चाहिए. Perpendicular ऐसे बाहर निकल के ऐसे जाना चाहिए. Clear? Here it is perpendicular, but it is not perpendicular. That means this field line must be like this. Here यहाँ पे अंदर जैसे जाना. Here यहाँ पे perpendicular. Okay, so that we will discuss later, but the thing is that what it is saying, based upon this particular property of conductor, what we can say that this conductor will be an equipotential surface, that means potential throughout the given region of the conductor will remain constant. V is constant. That means A, B and C, even if the center of the given conducting body, all will have same potential. All will have same potential. That means VA equal to VB, that will be equal to VC, and that will be equal to V. Clear? All will be having same potential. So that let us just check the options. So what will be the answer? So VC greater than VB, wrong. So wrong, and T also be wrong. So VA equal to VC, EA equal to VC. So this option D will be the correct one. Option D will be the correct answer over here. So here let me just draw. This will not be the figure. यहाँ पे ये परपेंडिकुलर होना चाहिए. क्लियर? ये भी यहाँ पे परपेंडिकुलर यहाँ पे होना चाहिए. ओके, फाइन. नेक्स्ट, okay, in question number 31, the warden in carrying a charge q once around a circle of radius a with a charge q at its center is. So here in this particular case, assume that a circle with radius, let it be a. Clear? And what we are doing, warden in carrying a charge q will carry a charge q, will move charge q. So let us assume that a charge q is initially located at a, and another charge q which is present inside or at the center. Clear? So both are positive charges. Then what is asking, what is the warden in moving this small q charge once around the circle? Once around the circle, that means once it will move, that means it will complete one circular rotation. It will complete one circular rotation on the circle. Clear? On the circular track. So here in this particular case, first of all, what we want to calculate, the potentials due to this charge. Here, potential due to the charge at any given location on the circular track. At this particular location, what is the potential? Potential will be V, and that will be KQ by A. What will be the potential at this particular location? B will be simply KQ by A. Clear? Because this location is situated at a distance of A. That location is also situated at a distance of A. That means at any distance which is at a point, or which is at any that means any location which is situated at a distance of A, that means radius, at that location potential will be. That means when we move a charge from here, which will be having potential B, to another location B, let it be B, which will also having same potential V, then what will be the potential difference? Potential difference is 0. That means this forms an equipotential surface. This forms an equipotential surface. If it forms an equipotential surface, then work done can be defined as Q into delta V, but delta V is 0. That means work done will be 0. Here, so work done in moving a charge over the equipotential surface is 0. So whether it is a complete circular path or any semicircular path or any 1/4 or 3/4 path over this equipotential surface, we go. So option D, the correct one.